Hi everyone, today we'll be looking at friction and in particular static friction, which means the amount of friction exerted between two bodies before they start sliding past one another. Okay, we'll also be looking at this concept of the coefficient of static friction, which in fact affects the amount of maximum friction that we can get between two surfaces before they start sliding. So in order to understand this static friction concept that I was mentioning earlier, let's have a look at this setup that I have used for the recording. What we have here is a box that is attached to a string, and this string is applying an amount of tension that depends on how much mass I add on this slotted mass hanger here. Now what I'm going to do is I'm gradually going to add these slotted masses on this hanger here to gradually increase the tension exerted by the string on the box. And we are going to see how much friction can we have between the box and the cable. The slotted mass hanger itself has a mass of 100 grams, right, which is roughly equals to a weight of 1 Newton, right? So that means that the current tension exerted in the string here on the box is going to be 1 Newton as well. Now the box itself is not sliding yet, right? So what this means is that friction must be preventing it from sliding. So that means this frictional force here must be 1 Newton as well. So let's have a look now. How does the frictional force differ as we add more masses to the slotted mass hanger? Okay, so here is where we start. So first, what I'll do is I'll add this 20 gram mass to the slotted mass hanger. So you can see that the box has not started sliding yet, right? Now with this extra mass here, the total tension that this string is exerting is 1.2 newtons. And since the box is not sliding yet, we can deduce that the frictional force has increased from 1.0 earlier to 1.2 newtons now. Okay, now let's have a look what happens when we add a few more. So this is another 20 gram mass. So again, the box does not slide. So now how much tension do we have? We have 1.4 newtons. No sliding still, so that means the friction has increased to 1.4 newtons as well. Okay? That was a 10 gram mass. So now we have a total tension of 1.5 newtons, and the box hasn't started sliding yet. So here we have friction. Friction has increased to 1.5 newtons as well. And here we have one more 10 gram mass. So at this point in time, I think this is where the box starts sliding, see? So what this means, right, is that when we increased the tension to 1.6 newtons, the maximum frictional force was probably somewhere just under 1.6 newtons, right? So let's put this as frictional force was slightly under 1.6 newtons, okay? So that means maybe our Fmax was around 1.599 something. Now, from this first video, right, what I want to show you is that the frictional force is actually a variable amount of force, and it can increase or decrease in response to the amount of force that's trying to make the two surfaces slide past each other. This tension is trying to make the box slide on the surface, and then the friction is going to increase in response to try to prevent it from sliding, but it will increase up to only a maximum value. Now, let's see what the effect is of having more weight on the box. So you see, in this example, what I've done is I actually added another 100 grams of mass on top of here. So what happens this time is that the entire box system here, there's a greater amount of weight downwards. And this also means that there is a greater amount of normal contact force exerted by the table on the box. You can see here that I've started this video somewhat in the middle of the experiment, and over here what I've done is I've already started with 140 grams and I'm adding another 50 grams here. So earlier on 1.4, 1.4, no sliding. Now there is a total of 190 grams there, so this corresponds to 1.9 newtons of tension. And you can see now with the extra weight on the top here, we have exceeded the previous maximum friction, and now we are at 1.9 newtons here as well. And the box still is not sliding. moving on, we are going to increase the amount of tension gradually, and we see that the frictional force does increase as well. And finally it drops. Now, the amount of mass that I placed there just before it dropped was, I believe, 2.3 newtons worth of tension. And so this is where the maximum friction was exceeded. So you can see, we seem to have found out that the amount of weight placed in the box does have some kind of effect on the maximum amount of friction that is available between the two surfaces. Okay, now let's move on to the explanation part. Right, so we've seen the demonstration, and from the demonstration we ended off by saying that the amount of weight that the box has seems to have an effect on the maximum amount of friction, right? Well, it turns out that it is not exactly the weight, but rather the normal contact force between the two surfaces that is what will affect the maximum amount of friction. So what we have here, right, is this is controlled by a constant known as the coefficient of static friction. Okay, and this coefficient of static friction is what controls the maximum amount of friction that is available between the two surfaces. From this equation, this graph, or rather this inequality in this graph, you can see the behavior that we observed in the video just now. When we increase the tension along this way, the amount of friction between the surfaces increases as well. Right, from here to here, let's say. Okay, and this will carry on all the way up to a maximum value of friction. And then when the tension applied is greater than the maximum amount of friction, then friction actually drops to a lower value. Now this portion here is known as kinetic friction, but that's outside the scope of this video. What I want to focus on is this value, right? The maximum amount of friction that can be applied between the two surfaces before the box starts sliding. Okay, and if we want to look at max value, then we can just convert it into an equation that looks like this. F max, maximum friction between the surfaces, equals to the coefficient of static friction multiplied by the normal contact force that is exerted between the two surfaces. Okay, now let's have a look at how to use this equation to solve some questions. Let's have a look at this question. Here we have two blocks, a lighter block and a heavier block. They are both free to move. There is a coefficient of static friction between the blocks, which is talking about this surface here. And the coefficient of static friction is this fraction 0.38. The surface below capital M is frictionless. This surface is the frictionless surface. So now what happens is we want to figure out what is the minimum horizontal force F, this one, needed to hold the small m against big M, and what is the minimum acceleration produced by this force. Okay, so what is happening here is that this is a frictionless surface. So when you exert a force F here, it's going to exert a force on the two box system. And because there's no friction at this surface, these two boxes are just going to accelerate towards the right. Now, at the same time, there is going to be an action-reaction pair of normal contact forces that is exerted between these two surfaces. Okay, one normal contact force exerted by big M on small m and vice versa. And this normal contact force between the two boxes is what is going to determine the amount of friction that is available between these two surfaces. Now, we want to talk about holding small m in place because obviously this box has a weight. Gravity is trying to pull it down. And so what is going to prevent it from going down? Friction. Friction between this large box and this small box. And this friction here is dependent on the amount of normal contact force that is exerted. So let's have a look at what this looks like in terms of a free body diagram. Whenever we are dealing with a mass acceleration problem, always try to draw a free body diagram first. So let's have a look. This is a free body diagram that I've drawn for the smaller box here. Okay, so like I mentioned earlier, we have this force F that's exerted to the right, and the normal contact force exerted by large M on small m that's exerted towards the left. And of course, we have this friction that's pointing upwards and the weight that's pointing downwards. Now, for this small m box to be held in place, what happens is that the friction upwards must be equal to the weight. This is so that the vertical forces are balanced. There's no net force in the vertical axis. So we can write this down in terms of friction equals to weight. Now, friction, let's say that this is the most extreme case and we are talking about the maximum amount of friction here. Okay, and so F max, if you recall earlier, F max equals to mu s times n. Okay, and we have from the question that mu s equals to 0.38, and so we can equate this to weight. Now weight equals to mg, if you recall. I hope you recall. And we can sub in the values for this, and we will find that the minimum normal contact force required is going to be 41.305 newtons, or 41.3 if you round off to 3SF. Now, we are supposed to find, based on this normal contact force, what is this force here. So, in order to do that, we probably have to do some simultaneous equations, right? Because there seems to be more than one unknown that we're dealing with here. So, turns out, if we look at the horizontal forces on the combined system, that means if we treat these two boxes as one system, then we can apply the usual F net equals to ma. So, F net in this case will just be this force here, F, right? And then this equals to m times a. Now m in this case refers to the mass of the combined system. So that's 1.6 plus 8.8, okay? And this is multiplied by a, the acceleration. Now a is unknown, f is unknown. We have two unknowns, right? Like I mentioned earlier. So if there are two unknowns, we need to have two simultaneous equations to solve. So what is another thing that we can do to come up with a second equation? We can look at the horizontal forces on small m, just this one here. So with reference to the free body diagram on the previous slide, if we look at the horizontal forces, F net equals to ma. Now F net, if you recall, there was a normal contact force towards the left. F net should be F minus this normal contact force n. And this should be equals to m times a. Now this block is undergoing the same acceleration as the combined system, right? So these two are the same a, right? Okay, so we sum in the value of m, the mass of the small ball is 1.6, and then we get an equation that looks like this, right? We found out n was this value in the previous step. So now we have two equations and we have two unknowns. We can just solve it simultaneously, which will give us the result. Acceleration equals to 4.69 and the force F required is 48.8. So I hope this was a useful lesson for you, because although this coefficient of static friction is not explicitly taught or explicitly stated in the A-level syllabus, I often see many questions that require this knowledge in the background to be able to solve. Right? This is one example, and I've seen other examples from topics such as circular motion. Okay, so thank you very much for watching, and I'll see you in the next video.